Hi there. So this is 13E and 13F, and this builds up to the central limit theorem, which also turns up in Unit 14 as well. It starts off by talking about the mean and variance of transformed or combined variables. And you might skip over this and just think, yeah, transformed or combined. They mean one and the same, right? But it's really important that you know the difference between transformed and combined variables. So if we're talking about transformed variables, let's just imagine that so we're really dealing with transformed and combined. Okay, so imagine we've got this case here. Say this is, for example, the results from a test from maybe your year group in terms of your mathematics tests. So this is what people were getting from their tests. Maybe I don't know. This is 50. I don't know. Maybe this is 40%. I don't know. Okay. So we can see how the year group is distributed there, put into little categories. So there's a frequency chart here. So potentially, I don't know, there's 20 people who get the score of between 50 and 55% in a test. Right. So if we decided that there was a question on that test which we thought was unreasonable, we might end up saying, okay, well, let's give everyone 5 marks because they definitely couldn't have got that question, and we're just going to add 5 marks onto everyone's questions, to everyone's results. In that case, what we're doing is transforming a variable. So if we add the same score on to every single value for x, so whatever value for x we have, if we say, look, let's add on b, let's add on 5 marks, then what's going to happen to the mean in this case, or e of x as well, the expected value of x, is that that's going to likewise increase by 5 marks. The whole distribution there is going to be it's going to be 5 further ahead. So the mean is going to be 5 further ahead. And if instead we decided we're still talking about transforming a variable here, if instead we're talking about this one test that the entire year group's at, and we said, actually, this test was out of 50, right? And what we're going to do is we're going to make it out of 100 instead, because people want their results as percentages. Then if your standard deviation here was, say, I don't know, let's say your standard deviation was 5, okay, or 10 potentially, so that 68% of all results were within one standard deviation of the mean, because it's looking roughly normally distributed. Then if we decided to times all the results by 2, so if we changed it to out of 100 instead, then the standard deviation is going to show us a much greater spread. So all of these results would end up looking something like this instead, right? So it would be spread out over a much wider period, twice as far up. Okay, so the spread of these would be twice as far spread out than the spread of these. So the standard deviation would be doubled as well. So if we do a combination of those things, if we said, okay, well, what we're going to do is we're going to double all of the results, and then we're going to add on 10. Well, in terms of the expectation, if we doubled all of the results, then the mean, which I'm using as just either x bar for the sample or mu for the standard deviation, or the expectation of this distribution. We've talked about the expectation a few times before. Mostly we can consider that to be the mean. So what's going to happen to the expectation of all of these different distributions? Well, if we doubled all of the values on a transformed variable, then what's going to happen is your mean in that case is going to double as well. So a mean of 50 now becomes a mean of 100 if we double all of our answers. And and if we then double and then add 10, then exactly the same thing is going to happen to the mean. Again, if the mean is, let's try and make it more sensible. If the mean was 35 out of 50, or the expectation was 35 out of 50, and we decided to double all the marks and add 10, well, we'd expect that we double the marks would become 70, so the average would become 70, and add 10 would therefore give us 80% out of 100, or it would change that mark into 80 instead. Okay, but what's happening in terms of the standard deviation? Well, in terms of the standard deviation, if we doubled all of these results, it would be twice as spread out up here. And if we added 10 onto all of those, this thing is which is twice as spread out, something like this, and then added 10 on, it would still be the same amount of spread out. So the standard deviation would remain the same. It would remain as double the previous distribution. Okay, so the plus b on the end has no effect on the standard deviation. And the times by a has the effect of on the standard deviation. But the a and the b transformations there affect both the standard deviation and the mean. So the plus b would add on to the mean there as well. Mean or expectation, I'm using them interchangeably. Okay, so that's transformations. So what are combinations? Okay, so it's really important that you get this. So combinations are, for example, if we had here some English results and then we had the maths results in the year as well. By the way, if I go slowly, then it doesn't draw nice smooth lines, but actually I think it's quite a nice graph there. So if we had, say, here's our maths results, here's our English results for the year group, and we can see the English results are on average higher. We could say, well, look, the maths results could be represented by X, and the Y is the variable for the English results. I'm not thinking about this transformation just at the moment. So we're then talking about, well, what happens if I want the expectation of two of those results added together? So I might be looking at adding one student's results and another student's results and so on. So I might take every student and add their results. I might say, let me add your English result to your maths result for every single student. Now, my expectation for adding x plus y would still give me e of x plus e of y, the mean, if you like, of the English results and the mean of the maths results added together would give you the mean of all of the results. Okay. However, what happens to the variance? So what would happen in the case of the variance? Well, when I add these two distributions together, I'll get something further up here. Okay, maybe that's 50, maybe that's 60. Maybe I'm getting something out of 200 now, I don't know. But the total is these two things added together. Maybe that's this mean, and and they're now up here. Okay, so the mean is now up here. And when I add them together, I'm going to get something which is much more flattened out in this case, because I'll have potentially some person here getting a low mark here, potentially getting a low mark in English. That's this person here. And someone high here might be getting, combined with this high result here, which would be getting this result here as well. Now, likewise, I could get a really high result there matched with a low result there, and it would be somewhere in the middle. So the spread of the combined variable, you can see, is more spread out than the spread of these two things here. Now, it is slightly more complicated in this case when we've got combined random variables than for us to just add the two standard deviations here or multiply the two standard deviations. In fact, this links through the variance. I'm not giving a proof for that just at the moment, but the formula in this case is that the variance of x plus y equals to the variance of x, and in that case, plus the variance of y. Now that's slightly different to saying the standard deviation of x plus y is equal to the standard deviation of x plus the standard deviation of y. In fact, that's not true. So yeah, let's go back. So there you go. So that's the rule which is linking these two things here. We'll come on to that a little bit more in a second. Just to sort of finish up on talking about the difference between transformed and combined random variables. Transformed random variables, again, we're talking about one set of results, which we're then saying, let's double everything. Let's add on something to all of them. Let's either times or divide or add or subtract something to that set of results. When we're talking about combining random variables, we're talking about putting two distributions together. Now, you can also put together, say, for example, x1 plus x22 variables, which you're taking results from the same distribution. It might be that we're taking two results here from the mathematics test and just adding them together. Now, there might be reasons as to why we would do that. So we could take from the same distribution itself. And in fact, this is going to lead to what's called the central limit theorem. That's going to turn up in the next exercise, essentially. And I think we might get there in this video as well. Okay, so let's have a look at what the book's got to say on this one. Let's look at the top of this page. So this was talking about the transformed variable. So let's just steal this and just talk around it briefly. So again, it's saying, look, if you take the expectation of ax plus b, so this transformed variable, so where we're timesing all of our results and adding something onto them, then the expectation is simply the expectation of the original distribution times by an plus b. Okay, and in terms of the standard deviation, if you were going to take the standard deviation of ax plus b, well, that would be the same as taking a times the standard deviation. This is nasty notation, by the way. I mean, probably I should be using sigma, okay? And then I've got just x in this case, and that was what I was explaining when I was saying how the b doesn't change the spread. Adding 5 onto all of the results in the maths class isn't going to change the spread, but doubling them all does. And that will double the standard deviation. Now, if that's what happens to the standard deviation, then remember the variance, this is equal to, let's see if I can write it down. So if I wanted the variance of both of these things, so the variance of this thing on this side, ax plus b, is going to be the square of its standard deviation. Now, squaring this, because the variance is the square of standard deviation, is the same as squaring this. So the square of this would give us a squared, but then squaring the standard deviation of x will then bring us back to the variance of x. So essentially what I've done there is I've squared both sides. So I've squared this to get this, and I've squared this side to get this and the variance of x, because this is the squared is the variance of x. Okay, now this is the preferred way of representing this, although this makes sense probably in terms of those graphs. This is the preferred way of doing it. And that's because it links with the other formula, which we're going to deal with in a second. Okay, all right, so let's just briefly look at some of the questions from the book on this. So let's see. So like, for example, the first one here, it says t is a discrete random variable with e of t is equal to 4.01. The variance of t is equal to 1.1. Find, and then we've got all of these things here. Let's just take some of this just to show this is actually really straightforward, simple stuff. Okay, so I mean, it looks hard, but it's really not. So if we were going to work out the expectation of this, well, we can just say that's the same as the expectation of t multiplied by 2.5 and plus 1. That's exactly what's happening here. We can use this thing here. So we're just using that result which we've just learned there. Likewise, if we wanted to work out the variance of this thing here, well, that's going to be the same as, you can ignore the minus 2, you can take the 5 squared outside, and then we've got 5 squared times by the variance of t. Okay, you're welcome to look through the other ones there, of course. They also go into talking about the binomial distribution and the Poisson distribution. Now, in this case, it says, well, what's the expectation of 3c plus 2? Well, that's also going to be 3 lots of the expectation of c and plus 2. And the expectation of c, remember that the expectation in terms of a binomial distribution, in this case, would be equal to np. We've done that before, of course, and likewise, the variance of c here is npq. That was a result which was given a couple of exercises ago. Q being 1 minus p. They didn't define it like that in the book, and I don't think they define it like that in the formula sheet. They do give these formulas in the formula sheet. From my point of view, MPQ is just nice to remember. Okay, so you're still going to need to use these formulas, but then you'll use them in conjunction with the new understanding. So, for example, the variance of 0.9t plus 1.2 is, this doesn't count, take the 0.9 to the front, square it, and then work out what MPQ is. Okay, right, and there was MPQ. Okay, so there we go. So that's transform variables. And now let's look at the results for linear combinations of random variables. Okay, so that is what we're seeing here. Okay, so Z is a combination of the random variables X and Y. And often you'll see in questions that they'll come up with new variables to then bring together other variables which are mentioned in questions. Okay, so in this case, they're saying pretty straightforwardly, but if we had E of X plus Y, that would be equal to E of X plus E of Y. Pretty straightforward. Now, if we have one lot of X and one lot of Y, that's what we're getting here. And likewise, if I said, look, let's put two of the maths result together with one of the English result, well, you can imagine the effect on the mean there, or the expectation, is times that by 2 and then plus 2 onto E, plus E of Y on. Okay, so that's just using this formula here. Okay, now, as I said before, this connects through the variance in this case. And it's important that with transformed variables, you connect through the variance. So here we can see that they give you this formula essentially. So they're saying that, when we looked at the simple case of the variance of X plus Y, so that's going to be equal to the variance of X plus the variance of Y. Okay, now if you have here the variance of AX plus Y, so if we've got A lots of the maths result put in with, so say, for example, let's do two lots of the maths result put in with one lot of the English result, then it's going to have the effect of adding 4 lots of the variance of X and then to 1 lot of the variance of Y, because it's essentially putting the standard deviation into this result twice, but the variance is that thing squared. Okay, now again, I'm not giving a proof of this, but it's connected via the variance, and you have to go with those formulas a little bit. So you can see what's happening there in this case. If I put a 2 in front of that, then I'm messing up there. I need to put a 4 in front of that because I need to square the A. Right, okay, I think that's probably given as a nicer box in the books. And there we go. Doesn't that look beautiful? So there we go. That's the version they have in the book. Okay, so I think from this point, we might have a little look at, I think I'm going to skip through a few of the examples in the book. And I think I might look at example 16. And so let's have a look at example 16 here. So that's E, so let's flick on. I think you've got most of what you need there to be able to flick on through this. And example 16, now let's check this one out. So here we go, here's a nice one. So this uses a lot of these ideas. So example 16, let's pick this out. So this is a nice example in context. So it's talking about packing boxes used by a removal company come in 3 sizes. We've got small, regular, and large. So we've got 3 variables in this case. After the boxes are filled, weights S, R, and L are modeled by normal distributions with these parameters. Okay, so standard deviation and the mean in each of these cases. So for example, S follows a normal distribution of mean 5 and standard deviation 2, so variance 2 squared. Okay, so it says 1 full box of each size is chosen at random. Find the probability that the large box weighs less than the regular box and 3 times the small box combined. Okay, so there's a sort of a new variable that they're coming up with here. I'll just try and write this one straight down. Right? So let's see. It says find the probability that the large box weighs less than the regular box and 3 times the small box. Okay, so when you're first looking at this, you're probably thinking, well, this is kind of nuts, right? I mean, I don't know what numbers to put in my calculator from this. It seems like there's lots of different distributions here. Okay, but there's one small trick to this, which is going to solve this question for you. And that's to bring everything over to this side. So either way round, really. So let's be consistent with what the book does. What do they do? Okay, so they take everything to the left-hand side, right? So they do L, take away R, take away 3 lots of S is now less than 0. That's now an equivalent question. Now, this thing we could call X or Z if we want to. So what we're really looking for is what's the probability that X is less than 0. Now, we've got distributions here which we can now add together. So we've got normal distributions which we can add together. And so we're talking about combined variables. And they're all normal distributions. We're going to combine these normal distributions. So our expectation in this case, the expectation of L minus R, I think my pen has run out again, R minus 3S, there you go. The expectation of that thing is going to be the same as the expectation of L minus the expectation of R minus 3 lots of the expectation of S. Okay, that's straightforward from the formulas, no problem. Okay, so we can just do the 30 take away 12.1, 30.2 take away 12.1, and take away 15, the 3 lots of E of S. For quickness here, I'm going to just pull that off here. So the expectation there is 3.1. So we're expecting that this answer should be 3.1. So the chance of it being less than 0 is going to be less than a half there. We're expecting that, on average, this should be about 3.1. This new variable that we've created here. In other words, the large box should be bigger than the regular box and 3 lots of the standard box, often, or the small box rather. Okay, and now we've got the variance here as well. So let's take that back. So I've run out of room. We've also got the variance here. So we've got the variance of X. What are we talking about here? We're talking about the variance of L minus R minus 3S. So again, we're going to need to use the formula for this one. So that's the variance of L plus, or if you like, plus minus 1 squared, which is obviously just 1. So plus the variance of R, and then plus minus 3 squared, so 9 lots of the variance of the smaller box. Okay, so again, if I sneak and have a little look at this one, we can see that that's coming to 110. Okay, so now I can get rid of all of this. Try and keep it in your mind. What were we doing? L minus R minus 3 lots of S. That's what we were calling X. So X is binomially distributed with a mean of 3.1 and a variance, not standard deviation, a variance of 110. Okay, now obviously you're going to need to square root that to give your standard deviation to your calculator. Okay, so now we're looking for, we've got the new distribution. We now need to find what's the probability that X is less than 0 in this case. We'll just put that into the calculator. So let's do that one. Let's check it out. So let's go to the calculator, to Scratchpad, to menu, to probability, to distributions, and then let's do normal CDF. And we've got lower bound of minus infinity, if you like. So you put in something extremely small like minus 9,999. And upper bound is 0. And the mean is 3.1. and the standard deviation is, and I'm going to put in the square root of 110. I'm not even going to calculate what that is. I'm going to put it straight into the calculator. So square root of 110, and it gives me 38.4%. So so we're getting 0.38377 carries on there. Okay. So let's check that one out again. Let's just check that we're getting that right. So there we go, 38.4%, 0.384 there. Okay, so it's pretty satisfying as a question, I think, when we're putting all of this together. So then for the second part, it's saying one full box and 4 small boxes are chosen at random. Find the probability that the total weight is more than 60 kilograms. So in this case, we can see that we're now doing one large box and 4 small boxes are chosen. Find the probability that the total weight is more than 60 kilograms. So we're going to need to do something similar again to what we did before. So I'm busy making mistakes again. Part B, I was thinking this is nice and easy. Part B says one full large box and 4 small boxes are chosen at random. Find the probability that the total weight is more than 60 kilograms. Okay, so I wrote this down. Not right. So I was just getting carried away with myself there. That's not right, because the large box add 4 lots of the small box is not quite what they're saying here. They're not saying times one of your small boxes by 4. They're saying let's choose 4 examples from this distribution. That's a bit like me saying we're not timesing all of our maths results by 4. We're taking 4 separate observations from that same distribution. So we're combining variables. We're not transforming variables there. So this is wrong. This is bad maths. So what do we need to do? Let's just take some of that back if we can. Okay, so in this case, it's slightly different. So for this one, our variable is, if you like, let's call it y. Y is equal to here a large box plus 4 smaller boxes. So that's S1 and S2 and S3 and S4. And that doesn't make a difference when it comes to the expectation, because the expectation is still going to be this plus 4 lots of this. We can't do better than that. But when it comes to the variance, remember that the variance formula says variance of x plus y is equal to the variance of x plus the variance of y. And here we've got the variance of x1 plus the variance of x2, so, or variance of s1 plus s2 plus s3. So we've simply got to add together all of those variances. So the variance in this case is going to be equal to variance of y, that is. It's going to be equal to the variance of L plus the variance of x1, not x1, s1 plus, and so on up to s4. Now, again, the best that you can do in this case is still 4. So the variance of L here is going to be 49, and then we're going to get 4 lots of the best case scenario, the best that we can come up with. The variance for each of these, because we're taking from the same distribution, is 4. We're getting 4 times 4 there. Now, remember that's different to if I'd have done 4L plus 4S, I would have needed to have split that up by saying, well, the variance of L plus 16 lots of the variance of S in this case. Okay, because in that case it's a transformed variable, not a combined variable. Okay, so that's what we're dealing with here. So this just caught me out there briefly, and you can see that it's easy to be caught out by the wording of these. And again, that's why it comes down to the fact that are we dealing with transformed variables, or are we dealing with combining variables? And that's a super important question. And that's what I opened up with, and I said this is the most important thing, and I'm falling into the trap myself here. Okay, from that point onwards, the question becomes easy, of course. Let's just check the answers on that one. So let's have a little look. So yeah, we can see that in this case, the variance here of all of these ones put together, 4 lots of 2 squared and plus 49 is variance is 65. So there's our distribution. And we're asking, what's the probability that this y, you can replace L plus S1 plus S2 plus S3 plus S4 by y is greater than 60 is then an easy calculation on your GDC. Okay, so I will go no further with that one. Okay, so that was a good question. It was a good question as a culmination of the questions in 13E. I think 13E comes next. Let's just check. If it doesn't come next, I'm wrong. Perhaps I'm wrong. Okay. There's 13E. (13E) was there. So yeah, okay, we've gone a little bit further than that. Okay. So combined random variables, let's take it a little bit further. So the last little bit here is talking about the central limit theorem, right? So that's this thing here. So central limit theorem. And in fact, I'm going to build this one up, but it says that the mean x bar of a sample of size n taken from any population with a mean of mu and a standard deviation of sigma can be modeled by a normal distribution with a mean of mu and a standard deviation of sigma over square root of n. There's a lot to unpack there, right? So central limit theorem. Next bit. Actually, I think I'm going to do this in another video, so I'll stop there. But that's going to be the next bit.